the name of this slide. And our aim is to find the fundamental regularities of fatigue crack initiation and its growth in very high cycle temperature. And now I will talk about in situ method of determining of irreversible fatigue damage accumulation during the fatigue growth. So this is a famous picture of high gravity, which shows fatigue loading, and it's for in this area we are working for, because in this area the probability of fatigue initiation from surface and from internal body of material is approximately equivalent. And there are two different mechanisms of this fatigue initiation. The first one is well known when the persistent slip bands activate from surface, go inside of material, and from lake crack. And about internal crack, there are some different mechanisms. One of these was observed by Sakai when around the inclusion of some different inside defect, there are little defect initiate and coalescent which is asked. And when special zone formulate, the crack formulated properly. So, but how to measure this kinetic of that defects? We used the fatigue testing machine, the USF 2000 by Shimadzu. It's resonant type machine. The system of horn specimen are in resonant. The maximum stress is situated in the center of specimen and maximum displacement in the end. And what we are doing, we put in the end of the specimen the magnetic gauge, which can measure the oscillation of that end. And we write the software which can calculate the first and second harmonic of that oscillation. And we found the good proposition of John Cantrell about that second harmonic. He took the nonlinear law of elasticity and introduced the nonlinearity coefficient, which connected with harmonic of that nonlinear law, and get that nonlinear parameter. Of course, the beta in the experiment measure a relative nonlinear parameter, which the beta is current parameter, and beta 0 is beta in the start of the experiment. And how to measure? We get the signal, fast Fourier transform that signal, we get amplitude of first harmonic and second harmonic, and by logarithmic that equation, we can get that here, that nonlinear parameter can get obtained by only that amplitude of first and second harmonic. Like that. And what we get? Here we tested different material, is titanium, titanium pure and titanium alloy, aluminium alloy, ferro, and so other material, and we get the same signal. What happens? First, it's a little growing signal of second harmonic. Then it's stabilization, and before the crack, it's flash going up. But in one material, which was preliminarily deformated, we have unusual signal when this nonlinear parameter growing down during the whole experiment, and then it's growing up, flashing very high. It's supposed that it's connected with relaxation of deformation, which were connected with preliminary loading, and by fatigue loading with little amplitude, it's a little relaxation, And when defects is going to interaction, it's formulate fatigue crack, which fracture the specimen. So then here it's one good picture. We can stop the experiment when the second harmonic is going up. So the first flashing going up to second harmonic, we stop the experiment, put it up, watching on it, and didn't find any crack. So that's why the crack was formulated inside the material. Then we put up the specimen in setup and started it, and we see how the second harmonic is growing up, and we connected this growing with growing crack inside the material. And then crack is going to surface and crashing the specimen. So by my colleague, we formulated mathematical model to describe that. And here is consecutive equation. This is parameter which can get from the static experimental, fatigue experimental, and dynamic. And here is scalable invariant structural parameter, which is ratio from characteristic size of nucleic defect and distance between this defect. And when it's this parameter going to 0, it's suppose that our structure is going to fracture. And when we simulate this parameter, this equation, we get a good agreement with experiment. Here we can see that defect is growing up, no interaction, and when it interacts, it's avalanche like growing defect and going to crash. So my conclusion is here in this slide. We can get new method which can analyze the defect kinetic inside of material and can predict the fracture when it's not occur from surface.
Thank you. Thank you very much.